Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. We are discussing about solid mechanics and materials subject. So in this, we have discussed about the slopes and deflections of a various beams. So how to calculate that slope at various points of a beam, and similarly the deflection also we have discussed about discussed in previous sessions about the various beams. So in previous session we have discussed about the methods. So how many methods are there to calculate the slope and deflection of a simply supported beams or cantilever beams. But in this today's session I want to discuss about the slope and deflection of a simply supported beams. The simply supported beam with a point load and simply supported beam with UDL and a variable load. So we will see. So for these beams, so how to calculate the slope and deflection. So how to apply in double integration methods. So before going to enter the main topic, you should know the outcome of this topic. The student should be able to utilize the Maxwell's reciprocal theorem and double integration method. We are discussing double integration method. Later we will see this Maxwell's reciprocal theorem and the moment area method for determining. So after completion of this topic, the module, the student be able to utilize these integration methods to they can able to calculate the slope and deflection of various beams. First we will see in this the slope and deflection of beams. So what do you mean by slope? Once again recall the definitions of slope and definitions, slope and deflection definitions. The slope, it is angular shift at any point of beam between no load condition and loaded beam. So its value is different at different points on the length of the beam. So it is represented by I or theta. The units are radians. So you know, so suppose the beam is subjected to point load, the cantilever beam. The beam is deflects like this. So it means so that the angle is theta. So this is slope. So its value is different at different points on the length of the beam. So represented by the I or theta. Similarly, the deflection, that is y or delta x. So it is the deflection is, it is the vertical shift of a point on the beam. So this is angular shift and the deflection is the vertical shift of a point on the beam between no load condition and a loaded beam. So its value is different at different points on the length of the beam. So it is represented by y or delta. So its units are mm. There is a limit for maximum deflection for any loaded beam. So in this, the slope is, there is a maximum limit for slope for any loaded beam, and deflection, there is a limit for maximum deflection for any loaded beam. So methods for slope and deflection already we have discussed in the previous session. There are many methods to find out the slope and deflection at a section in a loaded beam. So we are discussed the double integration method. Important. This is from the subject point of view. And the Maxwell's method we will see later. It will interesting to know that the first method is suitable for a single load. It may be point load or variable load. So whereas the second method is suitable for several loads. So double integration method is suitable for single load only. So in this, we have discussed about the simply supported beam with point load in the previous session by using the double integration method, how to calculate the slope and deflection. But today's session, we will see the simply supported beam with a eccentric point load. So not exactly at its midspan. So there is eccentric distance from its supports. So consider a simply supported beam AB. You know that both ends are supported of length L and carrying an eccentric point load W at C. From the geometry of the figure, we find that the reaction at A. So first reaction at A, RA and RB need to calculate. The simply supported beam AB of length L and carrying eccentric point load W at point C from its end, one end, that is distance is A, and from other end is B. Take a small cross section here, section with the distance X. So calculate the slope and deflection at particular section. See, the RA, the reaction force at A is W by L and RB is WA by L. So RA is WB by L. RA W into, so take moments about A, W into B by L. Similarly, RB is W into A by L. RB W into A by L. So here RA plus RB is equal to W into A plus B by L. So now consider section X in CB at a distance X from its B. So shown in figure. So such that the X value is less than the B. So that is the X is less than B. We know that the bending moment at this section. So calculate at a particular section the bending moment is RB multiplied with X. Mx is equal to RB reaction force multiplied with the distance. The CB, the distance X from B. So RB. So the RB is WA by L into X. So now you got this moment, the bending moment at the section. So already you know the bending moment at section EI into d square y by dx square. So as per double integration method, we have already derived this equation from the bending stress equation. Sigma by y is equal to m by I is equal to E by R. So bending stress equation. From this equation, we have derived this EA into d square y by dx square is equal to WAX by L. So the equation, write like this, and then integrate the above equation. So first integrate the above equation. So here a constant C1 is the first constant of integration. So find out the C1, you will get slope. So again integrate, double integrate, you will get deflection. The constant is, the second constant is C2. Find the C2 value by applying boundary conditions, that is constraints, where So first integrate the above equation EI into dy by dx is equal to WAX square by 2L plus C1 WAX by L. So WAX by L, so that is equal to W into X square by 2L after integration. So now C1 is the constant. Find out the C1 at the boundary conditions. What is the boundary condition? The X value is B and dy by dx is equal to IC. So the slope at C. So EI into IC. Now substitute X is equal to B. So WA B square by 2L plus C1. Now find out the C1 value. C1 is equal to A into IC minus WA B square by 2L. So now substitute this C1 value in above equation. In equation number 1, EI into dy by dx is equal to WAX square by 2L plus the C1 value EI into IC minus WA square AB square by 2L. Now integrate the above equation once again. So you will get deflection. So EI into Y. WX cube by 6L. Integrate the above equation. So integrate. Clear? So EI into Y into WAX cube by 6L and EI into IC into X minus WAB square by B square X by 2L plus C2. Now find C2 value by using boundary conditions. What are the boundary conditions here? Where C2 is the second constant of integration, we know that when X is equal to 0, Y is equal to 0. Substituting these values in equation 3, we get C2 is equal to 0. In equation 3, when X is equal to 0, Y is equal to 0. So put X is equal to 0, Y is equal to 0. So the term 0 and 0 and 0, 0. So finally, therefore C2 is equal to 0. So substitute the C2 is equal to 0 in above equation. So EI into Y is equal to WA X cube by 6L plus EI into IC into X minus WB square X by 2L. So the equations, second equation and fourth equation are required equations for slope and deflection at any point in the section AC. So this is the deflection. For deflection. What is the slope? The second equation. So this is second equation. Before integrating EI into dy by dx. So dy by dx is nothing but the slope at C, IC or theta C is equal to 1 by EI WAX square by 2L plus EI into IC. So that is dy by dx. You can write minus WA square B by 2L. You know, on the after double integration, we get C2 is equal to 0 and then substitute the required equations for slope and deflections obtained at any point in the section AC. At any point in the section AC. deflection and slope. So next one, a little concentration will show that these equations are useful only if the value of IC is known. So what is IC is means the slope at C is known. If the slope at C is known, these equations are useful. If you don't know the slope at C, not useful. So no need to, you can't calculate the deflections. Now consider at section X in AC at a distance X from B such that the X is greater than B. The X is greater than B. In previous case, the X is less than B. So take section here, the greater than the B. In previously, here you have taken the cross section. So less than B. So that bending moment at this section, calculate. So that is the bending moment at X is equal to W into X by L minus W into X minus B. So that the bending moment at X is equal to EI into D square by dx square is equal to WAX by L minus W into X minus B. So integrating the above equation, EI into dy by dx, so integrate. So integrate the EI. So take outside here TEI, integrate d square y by dx square is equal to integrate WA by L X minus W integrate X minus B. So EI into dy by dx and WA by L into X square by 2 minus W into X minus B whole square by 2 plus C3. So already C1 and C2 have used it in the previous equation. Now calculate C3 by using boundary conditions, the third constant of integration. We know that at C, what is the X value? X is equal to B. And dy by dx, that is theta, that is slope at point C. Now the EI into IC is equal to, substitute, the X is equal to B and dy by dx is equal to IC. In this equation for X is equal to B. And dy by dx is equal to slope at theta C or theta C. Now find out C3. C3 is equal to A into IC minus WAB square by 2L. Now substitute this equation in this above equation, EI into dy by dx is equal to WA x square plus 2L minus W into X minus B whole square by 2 plus C3. The C3 value now substitute. So substituting this C3 value in the above equation, we got EI into dy by dx is equal to W into A into X square by 2L minus W into X minus B whole square by 2 plus EI into IC minus WAB square by 2L. So integrating the above equation once again, you will get another constant term C4. Again calculate the C4 by using boundary conditions. So EI into Y W x cube by 6L W into x minus B whole cube by 6 and this term converted into EI into IC into X after integration minus WAB square by 2L into X plus C4. Now calculate C4. The fourth constant of integration, we know that when X is equal to L, X is equal to L and Y is equal to 0. So substituting these values in the above equation. X is equal to L and Y is equal to 0. So in this diagram, put X is equal to L and then Y is equal to 0. So substituting the above equation, so substitute Y is equal to 0. WA in place of X, substitute L. WA L square by 6 minus WA cube by 6 minus WAB square by 2 plus EI into IC into L plus C4. Now calculate the C4 value. So C4 is equal to WAB square by 2 plus WA cube by 6 minus WAL square by 6 minus EI into IC into L. Why? Because here X minus B is equal to A or X is equal to A plus B as shown in figure. So now again substitute this X minus B is equal to A. I have written an equation like this. WA square AB square by 2 plus WA by 6 into A square minus L square minus EA into IC into L. Now write this equation in A square into L square, A square minus B square. So A plus B into A minus B. So this in the form of A plus B into A minus B. So that A plus L into L plus CA. L plus CA into L minus CA. So A plus B into A minus B. So that again it's already given here L square minus A square is equal to L plus CA into L minus B. So that is AY. So here WAB square by 2 minus WAB by L into L plus here written this equation L square minus L plus A into L minus A only. So now WAB square by 2 minus WAB by 6. So L minus A is equal to B. Why? Because L is equal to A plus B. Here X is equal to L. So that L is equal to A plus B. As shown in figure, total length of the beam. Now substitute in place of L minus A is equal to B. L minus A is equal to B. So that's why you can write WA into B by 6 plus L minus A minus EA into IC into L. Again, write the above equation like this WAB by 6 into 3B minus L plus A minus EA into IC into L. Therefore, the L is equal to A, since A plus L is equal to A plus B, again apply in this equation, substitute A plus B plus A minus EA into I into L. So again you can write this equation WAB by 6 plus 3B minus 2A plus B, 2A minus B. So 2b minus 2a. So finally you can write WAB by 6 into 2b minus 2a minus EA into IC into L. So WAB by 3 minus, so here it cancelled 3 and B minus A into U. So this is the equation after integration and integration, and then substitute the boundary condition. So fourth constant already we have calculated, C4. Now substitute this C4 in above equation, in previous equation. So the previous equation, substitute the C4 value. So in this, the C4, EI into Y into WA x cube by 6L minus W into x minus B whole cube by 6 plus EI into IC into x minus WAB square by 2L into x plus C4. Here already you have calculated the C4 value. WAB by 3 into B minus A minus EI into IC into L. So here after substituting, you will get this equation WAB by, so this is the C4 term. So after simplify, the equations 7 and 9 are the required equations for the slope and deflection at any point in the section AC. In AC section deflection you got. So 9th equation and then 7th equation, this one. These are the required equations. So a little consideration will show that these equations are useful only if the value of C, that is IC, that is slope at C is known. So not to obtain the value of slope at C, let us first find out the deflection at C from the equation for section AC and CB. Now substituting x is equal to b in equation 4 and equating the same with equation 9. Clear? So now find out the deflection at C from the equations for sections AC and CB as shown in figure. Substituting in this equation 4, x is equal to b, equating the same with equation 9. So what is this 9 equation? This equation 9. So substitute, they equate with this equation. See here, WAB cube by 6L plus EA into IC into B minus WAB cube by L. This equation, substitute B in 4 equation. Equation number 4. This one. In this, substitute x is equal to b. Clear? So we are finding the AC, that is slow equation, the deflection at AC and CB. So equate these two equations. We'll get AI into IC is WAB by 3L into B minus A. So substituting the value of the EI into IC in equation 2. Equation 2. So what is the equation 2? So already we have derived this equation 2. The EI into dy by dx into WAX square by 2L plus EI into IC. So here EI into IC have calculated. So substitute the EI into the slope at C point in this equation. Clear? The equation 2 substitute, you will get one more equation. EI into dy by dx is equal to WAX square by 2L plus WAB by 3L into B minus A minus WAB square by 2L. So take common here W by 6L and we'll get 3x square plus 2b into b minus a minus 3b square. So again here 2b square minus 2ab minus 3b square. So you'll get W after simplification W by 6L into 3x square plus b square minus 2ab. So this is required equation for slope at any section in BC. We know that the slope is maximum at B. Thus the maximum slope substituting x is equal to 0 in equation 10. In above equation substitute x is equal to 0. If x is equal to 0, you will get the maximum slope for the maximum slope. So in this equation, substitute x is equal to 0. So in this term completely 0. Now you will get WA by 6L into minus b square minus 2ab. So you can write the equation, take outside minus and b square plus 2ab. Here you can write this term b square plus 2ab. We know the a is equal to L minus b. So why? Because L is equal to a plus b. And substitute in this b square plus 2ab, WAB by, so take common b outside here, WA into b by 6L, so 1b plus 2a. Clear? So substitute in place of a minus b here, W by 6L into b L minus a into L plus a. L minus a is equal to b and a plus b is equal to L, you know. So substitute in this equation and then you will get WA by 6L into L square minus a square. So you can write this L minus a into L plus a in the form of a square minus b square. So now the slope at B is equal to minus WA by 6EIL into L square minus a square. At A, WB by 6EIL into L square minus b square. At A and B. For deflection at any point in AC, substituting the value of EI in IC in equation 4, deflection you will get that EI into Y is equal to W into A x cube by 6L plus WAB by 3L into B minus A into X minus WAB square into X by A2L. So here simplify this equation. So you will get WAX by 6L equal to X square plus 2B square minus 2AB minus 3B square. So again you can write this equation WAX by 6L plus 3B square minus B square minus 2AB. X square minus B square minus 2AB. So again you can simplify for further simplification. So you will get minus WAX by 6L into L minus A minus X square. WAX by 6L into L square minus A square minus X square. So now finally you will get the Y value, L square minus A square minus X square. WAX by 6EIL. So for deflection at C, that is under the load, the substituting X is equal to B in the above equation. So what is the equation here? In previous equation. So in this, W into A, X is equal to B. Substitute X is equal to B in this equation. You will get W into A into B by 6EL into L square minus A square minus B square. We know that the maximum deflection will occur at CB, since the B is greater than A. Now for the maximum deflection, let us substitute the dy by dx is equal to 0. For maximum slope, substitute x is equal to 0. For maximum deflection, dy by dx is equal to 0. Therefore, equating the equation, the above equation, the 10th equation to 0. So, WA into WA by 6L into 3x square minus B square minus 2AB is equal to 0. So, again simplify. 3x square minus B, take common B and B plus 2A. And you know the L B is equal to N minus A. So, that is A plus B is equal to L. So, substitute. So, finally, we will get 3x square is equal to L square minus A square. So, from this equation, x square is equal to L square minus A square by 3. So, you can write the square root of L square minus A square by 3. So, this is for maximum deflection. Substituting this value of x in equation 11. In this equation, substitute the x value. So, what is the x? Square root of L square minus A square by 3. So, we will get the maximum deflection. For maximum deflection, WA by 6EI into L to square root of L square minus A square by 3 into L square minus A square minus L square minus A square by 3. X is equal to square root of L square minus A square by 3. So, after simplification, you will get the maximum value, the maximum deflection is WA by 9 root 3 EI into L to L square minus A square to the power of 3 by 2. So, this is deflection. So, like this, you have to calculate the slope and deflection of a simply supported beam with eccentric point load. Next one, simply supported beam with a gradually varying load. So, consider a simply supported beam AB of length L and carrying a gradually varying load from 0 at B, at 0 and W for unit length, that is A, as shown in figure. So, gradually the load is increased. So, take section with the distance x and find out the deflection and slope. From the geometry of the figure, so first of all, calculate RA and RB. WL by 3 and RB is WL by 6. WL by 3, RA and WL by 6. So, now consider section X at a distance x from B. We know that the bending moment at this section. So, from this equation, the reaction forces are equal to acting loads. That is RA plus RB is equal to WL by 3 plus WL by 6. So, here 2WL plus WL by 6. So, 3WL by 6 will get WL by 2. So RA plus RB is equal to WL by 2. So now calculate the bending moment at section X with the distance small x, RB into X minus WX by L into X by 2 into X by 3. So finally, you will get A into d square y by dx square is equal to WLX by 6 minus WX cube by 6L. So integrate the above equation. So integrate, you will get A into dy by dx to WX square by 12 after integration. So after integration, integrate. So WL by x square by 12 and WX to the power of 4 by 24L plus C1. So first constant. So find out this C1 by using boundary conditions. So where the first constant of integration C1, integrating the equation once again. So you will get A into y is equal to WX cube by 36 minus WX to the power of 5 by 120L plus C1x and C2. So find C1 and C2 and substitute in this equation. For C2 is the second constant integration. We know that x is equal to 0. Then y is equal to 0. Therefore, the C2 is 0. Then x is equal to 0 and y is equal to 0. So substitute x is equal to 0 and y is equal to 0. So 0, 0 minus 0 plus 0 plus C2. Therefore, the C2 is equal to 0. Clear? So now substitute the C2 value in the above equation. And one more C1 constant is there, that when x is equal to L, y is equal to 0. Substituting these values in equation 3. So equation 3 already we have derived here. So substitute C2 here 0, y is equal to 0 and x is equal to L. So you will get the C1 value. The C1 is minus 7WL cube by 360. So now substituting this value of C1 in this equation, you will get A into dy by dx is equal to WLX square by 12 minus WX to the power of 4 by 23L into minus 7WL cube by 360. So this is the required equation for slope at any section by which we can get the slope at any section on the beam. A little consideration will show that the maximum slope will be either at the support or A or B. Thus, for slopes A and substituting x is equal to L in the equation 4. For maximum x is equal to L in equation 4, we will get the maximum slope. So A into IA is equal to WL square by WL by 12 into L square minus W by 24L into L cube, L to the power of 4 minus 7WL cube by 360. So after simplification, we will get WL cube by 44. Now substituting this value of C1. So now the IA is equal to WL cube by 45 EI. Now for slope at B, the substituting x is equal to 0 in equation 4. So in equation 4, for x is equal to 0, slope at B. So you will get minus 7WL cube by 360. IB is equal to in radians. So minus sign means that the tangent at B makes an angle with AB in the negative or anti-clockwise direction. Now substituting the value of C1 in a third equation, you will get the y value. 1 by EI into WL x cube by 36 minus WX to the power of 5 by 120L minus 7WL cube x by 360. This is the required equation for the deflection at any section, by which we can get deflection at any section on the beam or deflection at the center of the beam, substituting x is equal to L by 2 in equation 5. So x is equal to L by 2 substitute, you will get the deflection at center of the beam 1 by EI into WL cube by 36 into L by 2 whole cube minus W by 120L into L by 2 minus 7WL cube by 360 into L by 2. Here minus sign means that the tangent at B makes an angle with AB in the negative or anti-clockwise direction. So now substituting the value of C1 in equation 3. In equation 3, so this is equation 3. Now substitute C1 value here. So minus C means that the deflection is downwards. So the value is 0.0065L W 651 WL to the power of 4 by EA. We know that the maximum deflection will occur where slope of the beam is 0. Therefore, equating the equation 2 or equation 4 to 0. Where slope of the beam is 0, there the maximum deflection will get. So now equate to 0 this equation WL square L x square by 12 minus WX to the power by 24L. So already we have derived here. Equate to 0, x is equal to, you'll get 0.519L. So now substituting this value of x in equation 5. So what is the equation 5? 4 and equation 5. EA into IA, this one equation 5. So we will get Y maximum. So after simplification, deflection will get, that is indicates minus sign indicates downwards, 0.00652 WL to the power 4 by A. So like this, to calculate the slope and deflection of various beams when subjected to various loads. So these are the references I have taken. Ramamurtham. Title of the book is Strength of Material, and publishers are Dhanapati Rai and R.K. Rajput. Title of the book is Strength of Material, and R.K. Bansal. Title of the book is Textbook of Strength of Material. And one more reference have taken R.S. Kurmi and Gupta. Title of the book is Strength of Materials. So you can take any one reference textbook for further more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.